20th century is the interaction of geometry and physics. The 21st century is the interaction of number theory with physics.
Hello and welcome to Maths on the Move, the podcast from plus.maths.org. I'm Marianne Freiberger.
And I'm Rachel Thomas. At the start of this podcast, you heard from Yang-Hui He from the London Institute of Mathematical Sciences talking about the impact number theory is going to have on physics. Now, the flow of ideas from mathematics to physics is definitely two-way. We've had lots of examples where discoveries in one field can lead to amazing results in the other.
Yeah, and one example that I'm familiar with is from the first half of Young's comment, the fact that the mathematics of geometry gave Albert Einstein the language he needed to define his general theory of relativity. This kind of interaction really shows the power of bringing researchers from different fields together. Now, Rachel, you recently talked to Yang about this, and I'm really intrigued by the idea that number theory could be impacting on physics in a similar way as geometry did.
Yes, I was talking to Yang as he was one of the organisers of a research programme last year at the Isaac Newton Institute in Cambridge, which brought together a really fascinating array of experts from lots of different areas, from people working in black holes or quantum theory. There were mathematicians, number theorists and computer scientists. It was really fascinating to speak to Yang about this, and he told me this amazing story that was all about the connections within physics and within mathematics, and then most importantly the connections between these two disciplines. As we'll see in this podcast, Yang told a story about the interplay between physics and mathematics that was really linked to the development of string theory. So we'll start off by asking Yang, what is string theory?
It is an attempt to unify the theory of the large, general relativity and cosmology, with the theory of the small, the theory of particle physics. And somehow it became this rich framework of quantum field theories that involves lots of cool math and lots of cool physics.
Okay, so string theory was an attempt to unify the physics of the very large with the physics of the very small. Now, we currently have Einstein's general theory of relativity, which gives a mathematical framework for understanding the force of gravity, which acts on large scales between planets and stars, for example. On the other hand, we have something called the standard model of particle physics, which uses a mathematical approach called quantum field theory, which Yang mentioned, to describe the other three fundamental forces of nature. So that's electromagnetism and the strong and weak nuclear forces. But what we don't have is a single mathematical framework that can describe all of these four fundamental forces. And such a framework is what people refer to as a quantum gravity.
So the research program that Yang was co-organising was discussing this search for a mathematical language for a quantum gravity. And the first place physicists look to see quantum gravity in action is in black holes, these mysterious regions in the universe where gravity is so strong not even light can escape. And as well as providing a bridge between the very large scales of gravity and the quantum scales of particle physics, black holes also provide a bridge between the worlds of physics and mathematics. So to see this in action, let's get back to Yang's story. String theory suggests that at the very smallest scale, the fundamental particles, such as electrons, they're not like we automatically think of them like little points. They're actually more like strings. And this very strange idea has lots of consequences. Some are very handy, like string theory, thinking of these fundamental particles as string-like, really makes some of the aspects of the maths used in describing the physics easier. And some consequences of string theory are really weird, like implying that rather living in the four-dimensional world we're used to, where we have three spatial dimensions and one dimension of time, string theory says we're living in a 10-dimensional universe, and it's just that some of these dimensions are curled up so tightly they're hidden from view. Yang explained the excitement and the huge expectations that physics had for string theory when it first developed.
that period, 70s and 80s, because of people like Edward Witten. There was this whole, everybody was getting into string theory. This is going to be the theory of everything, right? This is promised to be the theory of everything. It's going to solve black holes, quantum gravity, everything, you name it. And then people waited for 20 years and didn't find not a single thread of experimental evidence. But of course, finding experimental evidence is difficult, right? Because Higgs had to wait for, how long? Gosh, 50, 60 years, something like that. So, people are like, when are we ever going to see a signature?
So the lack of evidence was really getting the physicists down. But despite the lack of experimental evidence, string theory was still having an impact on the theoretical side of physics, such as in amazing concepts like the holographic principle, which occurred in sort of the late 90s, where gravity is actually an illusion conjured up by a quantum hologram. And string theory gave the physicist Juan Maldacena the answer he needed to give the very first example of the holographic principle. This really is a mind-bending idea. You can find out more about some articles on plus.maths.org. We'll put a link in the show notes.
Yeah, these ideas are really quite mind-bending, as you say. But meanwhile, exciting things were also happening in mathematics. Now, you mentioned earlier that string theory says that we live in a 10-dimensional world and that the extra dimensions are hidden. They're very tightly curled up. And the question was, how could that be possible? What kind of geometric object would allow dimensions to curl up like this? Now, luckily, mathematicians had discovered what are called Calabi-Yau manifolds. They discovered them independently of the physicists. And they helped to explain how these extra dimensions can be hidden. And the mathematician Xintun Yao actually won the Fields Medal for it, which is one of the highest honors in mathematics, in 1982. I was lucky enough to meet Yao in 2010, and he told me this interesting story about how he found out that physicists were interested. He said that he was in San Diego with his wife, looking out at the ocean, when his phone rang. That was back in 1984. And it was his friends Andrew Strominger and Gary Horowitz. And they were really excited because string theorists were building up models of the universe, and they needed to know whether those Calabi-Yau manifolds really existed. And Yao was very happy to confirm that they did exist. So this is another example of how mathematics helped to answer a problem in physics, in particular in string theory. It provided the geometry, the geometric structure that was needed to hide extra dimensions. And Rachel Young told you more about the exciting connections being made between string theory and pure mathematics.
And then that had about 10 years of development when they realized, wait a minute, this is giving so much rich mathematics. It's kind of funny. So by the early 2000s, you talk to any algebraic geometer, he or she will be like, I'm 100% convinced that string theory is right, because we have never encountered a theory of physics that's given us so many problems to work on.
So the impact of string theory in mathematics really convinced mathematicians that string theory was going to be useful in both maths and in physics.
You just ask any mathematician, will be like, well, you guys are absolutely on the right track, because we cannot imagine another theory. It's like kind of analogy would be like how a pure mathematician, if one could make a division like this, would have felt about the development of calculus. Newton had to be on the right track because this tool he invented in order to understand the physical world was revolutionary to pure mathematics.
So what were some examples of this rich mathematics that mathematicians were so excited about?
Well, Yang told me about one example where string theory helped to solve a long-standing counting problem in geometry, something known as enumerative geometry. It was such an important and long-standing problem that the mathematician David Hilbert actually included it in his famous list of 23 unsolved problems he announced back in 1900. Here's Yang again.
So there's this classic problem of what's called enumerative geometry, which goes back to like Apollonius. I know it's just simple problems like in a plane, 2 points will fix a plane, fix a line. 3 points will fix a circle or anything of degree 2 and so on like this. But then you have asked more complicated problems like, if I gave you one circle and a couple of points here, how many circles can you construct that's tangent to this circle and passes through? That kind of, this kind of enumerative problems. And all the way through the 19th century, this was, part of this program. Schubert calculus is invented, and Hilbert even asked this one of his foundational problems in his 23 problems, is that does there exist a general method by which one can solve this kind of enumerative problems? This is a pure problem in geometry. And then it turned out in the 90s, early 90s, people like Philip Candelas and people like Brian Greene and collaborators realized, at least for a huge class of geometries, Claviel geometries, to solve the enumerative geometry problem for this, all you needed to do was to create a string theory on it. And they wrote down a partition function using physics ideas whose coefficient expansion exactly enumerated this. And when that came out, the math was completely blown away, because they were like, oh my God, these physicists have got on something that we couldn't even dream of a technique to solve.
So it's not just that mathematics was providing string theory these fantastic structures and methods and language.
Yeah.
It's that string theory was actually able to solve problems in mathematics that hadn't been solved.
Exactly. So, and I think there has been nothing like that in any of the contenders of cutting edge theories of physics. There've been things like loop quantum gravity, which I don't know that much, and then there's things like spin foam and all various other theories of fundamental physics. But there's nothing been like this. They haven't solved any problems in fundamental math. They use a lot of fancy math, of course. Any physics theory will ultimately use a lot of fancy math. But something very different about this idea of string theory is just constantly solving these crazy problems.
You heard Yang mention partition functions being used to solve this problem. Partition functions are really fascinating as they appear in both mathematics and physics. Here's Yang again.
So a partition function is very simple. So in physics, a partition function is just an organizing tool. So a classical one is, you have a physical system. It has, say, various energy levels. And the partition function is just, it sums the number of states given particular energy. So it's a hard problem. Like, how do you count how many possible states are there at a physics? This is stuff that goes back to Kelvin. They were thinking about, in a room filled with gas. What is how many states are there for their at this energy level? It's called partition function because at the end of the day, it comes down to a combinatorial problem of how to partition the number of states into particular states. I think that word is actually borrowed from mathematics. So a good partition problem is like, how many ways can you write a given positive integer as sum of positive integers? Right, so like 4 is equal to 1 plus 1 plus 1 plus 1. It's also equal to 1 plus 2 plus 1. And you can count this, and that's called the partitions of 4. But that problem, this kind of idea solved the problem that physicists were thinking in statistical physics, where they organize this. So a partition function is a generating function, which is an infinite series that counts the number of states given particular energy level. So you can park it. So physicists have been thinking about this since Kelvin.
So partition functions appear in both number theory and in physics, and we'll get back to them shortly. Okay, now Yang has another fascinating example of the impact of string theory on pure mathematics, and this involves something called the moonshine conjecture. This poetic-sounding conjecture was work done by the mathematicians John Conway, John Mackay, Simon Norton, and John Thomson. They conjectured that there was this incredibly deep link between number theory and another area of mathematics called group theory, which is essentially the mathematics of symmetry. Now, one of the greatest mathematical achievements of the last century was in group theory, and it was a result called the classification of finite simple groups, which, loosely speaking, imposed some order on a part of the mathematics of symmetry.
Now, one of the other great achievements in the last century, which you actually probably might have heard of, was Andrew Wiles's proof of Fermat's last theorem. It's one of the few pieces of mathematics that, when it got solved, hit the headlines, hit the news. To prove Fermat's last theorem, Wiles used something called modular forms. These are mathematical objects that are symmetrical in a kind of inordinate number of ways, incredibly symmetric. Modular forms have become one of the most important tools in number theory today. So what Norton and Conway suggested in their conjecture was that there was a deep connection between a particular type of modular form and a particular special case of the classification of the finite simple groups. Here's Yang again.
It was completely crazy that these two fields should even be related to each other. It's unthinkable. It's so unthinkable that Conway called it moonshine, right? It's too crazy. And the ultimate proof of the moonshine conjecture, which got Borcherds the Fields Medal, he used a technique from string theory. He somehow learned about this idea from conformal field theory from people like Goddard at Cambridge. Why? I guess he was just bored and wanted to listen to someone. Hey, what's in the buzz? And he got that technique, and then that technique was what's needed exactly to prove the moonshine conjecture.
So again, here is an example of string theory unexpectedly providing the tools needed to solve a really important problem in pure mathematics, and particularly a result in number theory. And it's using this idea of modularity, which, as Yang explains, is an incredibly important idea in number theory.
But what's remarkable is that this modularity, this kind of ideas of modularity, creeps up in mathematics over and over again since at least Gauss. Lots of the most profound results in mathematics come from this property. For example, Fermat's last theorem. Right? Fermat's last theorem was able to. Wiles's great contribution to that was to prove something much more broad than Fermat's last theorem. Wiles proved the Taniyama-Shimura conjecture, which is now known as the modularity theorem. Very, very profound stuff. But what is really amazing in the 2010s is that black hole partition functions coming from string theory also exhibited modularity behavior. So now you're really in the deep land of mathematics. Since it's already had such a fantastic track record, right? It solved problems in numerative geometry, it solved problems in moonshine conjectures, in representation theory. If it gets into modularity, it will at some point give deep and profound results in number theory.
And is there, because I know you mentioned Ramanujan before, because he did work on partition functions in terms of numbers, number theory.
Yes.
So is there a connection between the work he was doing there and the partition function work in black holes?
Absolutely. Yeah. It's. I think I don't work on this area, but my understanding is exactly the partition functions. It's very confusing. They're both called partition functions, but the partition functions showing up in black holes are the kind of modular functions that solve partition problems from Ramanujan.
I see. Oh, that's very interesting.
So counting what's called counting microstates in black holes. Because it's an entropic system. Counting microstates in black holes, it is like counting certain partitions of integers in very constrained partition problems in integers. So this is why there are all these papers written. And there's a big, it's still a very, very active field of research, which is, sort of modularity behavior for black hole partition functions.
That was Yang-Hui He from the London Institute of Mathematical Sciences telling us about bringing together the ideas of black holes, of thermodynamics and entropy with Ramanujan's results in number theory. But there's still another chapter to our story. Yang's contribution to the Isaac Newton Institute program, which was called Black Holes, Bridges Between Number Theory and Holographic Quantum Information, is actually slightly different. He was bringing his expertise in applying artificial intelligence to mathematics and physics, and in particular to helping us make new and meaningful conjectures.
That sounds really intriguing and fascinating. So you will be able to hear about Young's research and his recent work on the evocatively titled murmuration conjecture in the next podcast. And you can find links to all of the things we talked about in this episode in the show notes. And that's it for this podcast. Thanks for listening, and bye-bye.